In today's experiment, which is experiment number 5, we're going to determine the atomic mass of a metal. In particular, we are going to determine the atomic mass of zinc. In order to do that, we're going to react zinc with hydrochloric acid to obtain zinc chloride and hydrogen. The hydrogen that we are going to obtain is going to be in the gas form and is going to be collected, and its volume is going to be measured. According to the chemical equation, the amount of hydrogen that we are going to collect, expressed in moles, is going to be equal to the moles of zinc we had at the beginning of the reaction. So remember, moles of collected hydrogen is going to be equal to the moles of zinc that we put at the beginning of the reaction. Next, by knowing the mass of zinc that we weighed and dividing it by the number of moles of obtained zinc, we can calculate the atomic mass of that metal. In the experiment, zinc is going to be here, wrapped with a copper wire so that it doesn't disperse in the whole solution. What we have in the beaker here is the hydrochloric acid solution. The hydrogen is going to be collected in an inverted graduated cylinder. And this here is the space where the hydrogen is going to be contained. In this space, we have hydrogen gas, but at the same time, we have vapor from the water below. So we have the pressure from hydrogen and we have the pressure from water. The pressure inside this void is going to be equal to the atmospheric pressure when we equal the level of the liquid in the cylinder and the level of the liquid in the beaker. Which means that we know the total internal pressure, and from that total internal pressure we can calculate the hydrogen pressure. To obtain the pressure of the water vapor, by knowing the temperature of the water, you're going to use a table that is at the end of your lab manual, in which you have listed the vapor pressure of water as a function of temperature. And you're going to subtract it from the total pressure, which is going to be given to you by your instructor. Hence, from what we just saw on the figure that illustrates the experiment, the pressure of hydrogen that is going to be trapped is going to be equal to the total pressure, which is going to be the pressure on the lab, minus the vapor pressure of water that you are going to get from a table in your lab manual. After obtaining the hydrogen pressure, the number of moles of hydrogen is going to be calculated using the ideal gas equation. And in that particular case, the number of moles of hydrogen is going to be equal to the pressure of hydrogen times the volume that you're going to measure experimentally, divided by R, which is the universal constant for the gases, and the temperature at which you conducted the experiment, which is, in this case, the temperature of the water, the same one that you use to get the vapor pressure of the water. In a 1000 milliliter beaker, fill it up with about 600 milliliters of water and submerge a temperature probe on it. Your instructor is going to give you instructions on how to do it. And then on the screen of the computer that you have in your lab bench, you're going to read the temperature of the water and the atmospheric pressure, which is going to be your total pressure in the experiment, and write it down in your lab manual. Go to the appendixes of the lab manual, and on those appendixes you are going to find one which is appendix E, in which you have listed the vapor pressure of water in millimeters of mercury as a function of temperature. Looking at the temperature you got for the water, which was 21 degrees, we can see that at 21 degrees the vapor pressure of water is 18.65 millimeters of mercury. Write it down on your lab manual. For this experiment, we're going to use an analytical balance in which we're going to have an accuracy that is going to be 0.1 milligrams or 10 to the minus third grams. In other words, 4 decimal places. So make sure that when you write down the mass of zinc, you do it with 4 decimal figures. Take a piece of zinc, has to be only one piece, okay? Cannot be 2 pieces, has to be only one, and weigh it in the balance. This one in particular weighs 0.1615 grams. It should weigh between 0.15 and 0.20 grams, so this one is okay. Now we are going to wrap the zinc piece that we just weighed using copper wire as to make a cage so that the zinc doesn't dance around when we are doing the reaction. For that we use a piece of copper wire and start to wrap it around the zinc piece like I'm doing it right now. And this is the final setup in which we have the zinc inside, as you can see it here, and it's all wrapped with copper wire. Now what we're going to do is to drop it in the beaker and where we have the water. Okay. Next we're going to fill the graduated cylinder all the way to the top with tap water. Okay. When I say to the top, is completely up to the full capacity, and put a piece of absorbent paper on top of it. If we have air bubbles, we have to add a little bit more water, so that when we put the paper on it, no air bubbles are formed. If that's done correctly, when you turn the cylinder upside down, it shouldn't drop. So move it quickly to the beaker, and now you have a cylinder that is completely filled with water. Here, to take out the piece of paper, and now we have the cylinder completely filled with water, the zinc on the cage, on the copper cage, and what we're going to do is move the cylinder and put it on top of the cage. Okay? Now we put a funnel with a long stem so that the end of the stem is as close as possible to the copper cage that contains the zinc. We're going to use that funnel to pour the hydrochloric acid that is going to dissolve the zinc in the reaction that we are studying today. In a 100 milliliter beaker, pour about 50 milliliters, which will be half the beaker, of 6 molar hydrochloric acid. And pour it quickly. Okay, you can see now that a gas is evolving. You can see the bubbles, and the bubbles represent the hydrogen that is being evolved from the reaction, and that hydrogen is being trapped here at the top of, or the bottom in this case, of the cylinder. So you can see that the hydrogen that is being collecting is pushing the water down. You have to wait now for about 20 minutes until you see that no more bubbles are coming out of the copper cage. Okay, we have reached the end of the reaction. You can see that the bubbling has stopped. Now, just the level of water outside the beaker, so that the level outside on the beaker, the level on the beaker and inside the cylinders are equal. For that, we take a beaker and pour water until the two levels are the same. Now that the water inside and outside the cylinder are level, we read the volume of hydrogen that is being collected. In this case, the volume is 63 milliliters. The way we did the first trial, we're going to do a second trial. So now we have that the atmospheric pressure in the lab is 760 millimeters of mercury. The temperature of the water and the lab is 21.27 degrees centigrade. And the vapor pressure of water at that temperature is 18 millimeters of mercury. Here we have the results of the first trial. Remember that the volume needs to be converted from milliliters to liters, and the corrected pressure after we subtract the vapor pressure should be expressed in atmosphere in order to use the ideal gas equation. The gas constant, R, you have to look for it in the literature. However, the value that you have to use for this experiment is 0.08206 liters atmosphere per mole Kelvin. On the second trial, we have another weight for zinc and the collected volume, and you have to complete the rest of the table. And after that, in the post-lab, you have to do the calculations to come out with the mass of zinc in trial 1, trial 2.